Hello, calculus. Tonight is November the 10th, and we are looking at the first derivative test. So, let's see what's in store for us. It starts out with a lot of blab, so I just wrote it out ahead of time. So while I'm just reading it to you, you can be writing it, and it is in theory the first derivative test. So we'll talk about what the theory means and then do two examples, and I'll ask you to do one. So grab your comp book. The first part, the first statement in the first derivative test is if f prime of x changes from a negative to a positive. So we're talking about a derivative, so we're talking about a slope. So if the slope of a curve changes from negative to positive, negative slope, positive slope. So if it changes from a negative to a positive at some value c, then f has a relative min at that point c, f of c. And then the second part of the first derivative test, if f prime of x changes from positive to negative, so at c, then f has a relative max at c, f of c. And lastly, if neither of those happens, if f prime of x is positive on both sides of c, or negative on both sides of c, then cf of c is neither a relative max or relative min. All right, sketch that down, and if you can't see that well, I did write pretty small. You can leave space in your comp book and it's right in your book. You can get it tomorrow. All right, you can stop the video if you're still writing. I'm going to erase and go from there to discuss this. It takes so long to erase this. There we go. Okay. Continuing on, let's see what that means. I kind of showed you with my arm and my elbow. Let me show you with a quick sketch. So if I have a function that goes like that, and right here, of course you can see right away it's a minimum, but we're saying that we don't have a picture of it in front of us. But look what happens to derivatives. So when we don't have a picture in front of us, let's see if we find a better marker than that. It's floating around here somewhere. Nope, nope, nope. All right, I'm gonna have to find a marker. All right. Doubt if this one will do any better. Nope. All right, I'll go to the least worst one. All right, here's the derivative at this point. You can see is a negative derivative. So if it's going from negative, if we're going from left to right, and it switches from a negative derivative to a positive derivative, then we must have a minimum point in between. That works the other way for a maximum. On the left, we have a positive derivative. On the right, we have a negative derivative. And then sometimes we have a function that does not look like that. It looks like, say, this. And right here, actually the tangent line is flat, so we do have a zero derivative. It is a critical point, but the derivative here is negative, and on this side it's also negative. So that indicates it is not a local max, or I'm sorry, it's not a local max or a local min. And that goes the other way as well. If we have a function which has a critical point there where the derivative zeroes out, but look to the left and you see a positive, and to the right you see a positive. So again, that indicates no relative max or min. All right, so let's do one. See if I can get my space back. All right, let's do f of x equals 1/2 x minus sine x. Let's go with that, see how that works. And we're going to look at it on an interval from 0 to 2 pi. That's where we're interested to see if there's max or min values. So first the step is take the derivative. So we get 1/2 minus cosine x. And set that equal to 0. I'll move the cosine x over, and I get 1/2. Looking at the unit circle, where's the first coordinate in 0 to 2 pi? Where's the first coordinate going to be 1/2? I'm going to go over 1/2 and up square root of 3 over 2. So that's right there, and that happens at pi over 3. And is there another value where that happens? First coordinate 1/2 is also down here, and that is 1/2 over negative square root of 3 over 2. And that is how many pi? 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. This is 5 pi over 3. So these are our critical values, and we found them by setting the derivative equal to 0. Where else do we look for critical values? Where the derivative doesn't exist. But this is a trig function. It's a smooth curve. There's no places where there's an asymptote in a sine curve, and there's no holes or skips or sharp turns. So this is all the places that we need to investigate. So now I'm going to draw a number line, and I'm going to put in it, since our first value is 0, then our interval, then pi over 3 comes next, then 5 pi over 3, and the last value I'm interested in is 2 pi. So these are the ones we're looking at, and just like last night, we're going to take a test value. So the test value that I'm interested in between 0 and pi over 3, which is between here and here, I'm going to pick pi over 4. And when I do that test value, do you remember where I throw the pi over 4 in? This is the test value. I'm going to test pi over 4. I put it into the derivative statement. 1/2 minus cosine pi over 4. Cosine pi over 4 is root 2, and 1/2 minus the square root of 2 over 2 is a negative number. So I won't take time to verify that, but you can do that for yourself. A number, a test value in between pi over 3 and 5 pi over 3 could be just pi's in between there. So let's test pi. And you don't have to use the same test values as I do, because every value in between these two will have the same sign in its first derivative. So pi, we put that in here, 1/2 minus cosine of pi. Cosine of pi is -1. So we have 1/2 minus a -1, so that's a positive value. And the test value here between 5 pi over 3 and 2 pi would be like 7 pi over 4. 1/4, 2/4, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, yes, 7/4 pi. So I'm going to plug that in as my test. And the cosine of that is square root of 2 over 2. 1/2 minus square root of 2 over 2. How's your unit circle doing? Has it survived this year in calculus? Is it still there? it turns out to be like this section, it's negative. So we know that we have in this area, we have a negative sloping curve, and when it gets to pi, it's going to be zeroing out here, and then a positive sloping curve, and then it zeroes out here, the derivative, and then it's be a negative sloping curve. So this must be a local min. This must be a local max. So at pi over 3, we have a local, or what's that, relative, same idea. It's a relative min. And because the derivative went from negative to positive, you don't even have to sketch it. I just did that to show you what it would have a similar shape to. And this one here went from positive to negative, so we have a relative max. Alright, so that's cool. I'm not sure how long I've talked, so let me shut this down and go ahead and do another example on part 2, and I'll leave one for you, so till we meet in a few seconds.